Hey class, so this week we are looking at distributions as kind of the main topic for Module 2. And the first thing that we want to look at here are what we call frequency distributions. And so what I have here is, on the left, we've got some data, all right? So we want to plot a frequency distribution of the resting heart rate, just as an example. And these are all just numbers that I kind of made up. So this isn't from some data set, but it's just numbers that I just kind of put together. And and so I've got all these numbers, and the first thing that we want to consider is, why even bother, if I have all my data, why even bother building a frequency distribution in the first place? And the reason why they're important is because if I want to understand the data that I've collected, I need to be able to see it in some visual way, or at least organize the data better than what I can find in just some data table that might just contain the data in the order that it was collected. If you look at this data table, it's not even organized from least to greatest. It's just all of the data sitting in one spot. So for statisticians, one of the ways that they deal with and organize continuous data, because if you look at this, right, this is resting heart rate, so this is a ratio measurement of data, because number one, there is an absolute, there is a true zero, okay? Your resting heart rate can be zero. You would be dead, but you can have a resting heart rate of zero, and that does mean that the heart isn't beating. And it also doesn't make sense to have a heart rate that would be negative, okay? So that's going to put that into the ratio category. And it's a continuous quantitative variable, okay? Frequency distributions like this are used for continuous data. So what we want to look at is a little bit of how this is built. So number one, with these types, you're going to have a range, right? So I've picked ranges of values, and then you're going to write down the frequency, or how often does a number occur within that range. Okay, that's what the frequency is talking about, right? If you look at the definition here, it's distributions where the values are plotted against their frequency of occurrence. My arrow's in the way of that a little bit. So let's go over to our data table. Oh, I guess a couple more things. If you look at these, look at each of these ranges, okay? There's some things that are really important. Number one, it's a continuous range, okay? I go from 60 to 61, 80 to 81, 90 to 91, okay? So there's no break. You can't, if you're going to build a frequency distribution, it cannot include a break in that range. Otherwise, it's not a true frequency distribution. Notice that I don't include 0 up to 51, and that's fine. But over the range that I'm interested in, there is no break in that range. So that's important. The other thing that's important is that each of these ranges are evenly distributed, right? 10 values fit, so the way that I built this, 10 values fit into each range. You don't have to pick 10, it can be a different number, but for the point of what I'm doing here, we're going to look at 10, okay? So then to actually build the distribution, I'm going to go to my data set, and so here's all the numbers in my data set, and they're really great. And I'm gonna fit numbers in here. So let's find everything between 51 and 60. So I comb down and I'm like, okay, here's 1. So there's 1. Okay, there's only 1. So there's 1 value within the range of 51 to 60. Okay, so then I go against 61 to 70. Here's 1, 2, 3, 4, 5, 6, 7. Okay, there are 7 of those. Then between 71 and 80, 1, 2, 3, 4, okay, 4. 81 to 90, 1, 2, 3, 4, and, oh, I missed one, 5. Or did I count that? Hold up, let me look at that again. 1, 2, 3, 4. Oh, there is only 4. I just didn't mark it. And then there's 1 and then 91. Okay, so that's what the frequency distribution looks like. I can now... This doesn't tell me anything about the specific... That's the thing. This doesn't tell me anything about the specific or individual data points, but it does give me a pretty clear picture of what my distribution looks like. I can look at this and immediately see that, oh, look, most of my data falls between 61 and 70 beats per minute. And then I've got a little bit more in the next bracket and a little bit more in the one after that, and then it falls off again. And that's the beauty of the frequency distribution, is that it allows me to quickly see, like, where's my data concentrated and what's going on within the data that I collected. So if I wanted to, I could organize this a little bit differently. Notice that this plot, this new one, all I've done is I've changed the range. Okay, these ones are organized or grouped in 5s, right? So instead of grouping them by 10, I'm grouping them by 5. You can build that range however you want, right? Whatever makes the most sense to you in your study. And this plot is going to look a little bit different than the one before, right? So then I could come back to my data to see what fits. Anything between 51 and 50. And I go down and look, or 51 and 55, there's one value there. 56 and 60, there are 0 values there. 61 to 65, so there's 1, 2, 3, just 3 of those. 66 to 70, 1, 2, 3, 4. And then 71 to 75, 1, 2, okay. And so you can look at this and, right, and I would keep going, right, and I would fill this out for the rest of my data, but you can see that this looks a little bit different. It's telling a slightly different story than what this told. So depending on what you want to look at and how you want to interpret your data, you're going to kind of build and arrange your frequency distribution a certain way. Now, as these ranges get smaller and smaller, right, you're spreading your data out, and you're going to look at it, interpret it differently. If this range was only 1, right, if this went 51 and then 52 and then 53, that would tell a much different story than what I'm seeing either here or here. So as you're looking at this, right, the way that you interpret these changes based on how you've collected your data. And then when the data you're dealing with is numeric like this, when it's quantitative, you're going to plot it, right, you're either looking at interval or ratio data. You're going to plot it in a histogram. Okay, and I'll talk a little bit about what a histogram is in a couple of slides. So the next thing we want to look at here are a frequency distribution for data that's more categorical. Okay, so you see over here on the side, I've got this list of favorite ice cream flavors, right? So let's say I sent a poll through a random class, and this is the data I got back, right? One kid likes chocolate, another likes strawberry, another likes vanilla, right? So I've collected this data. Now this is categorical, right? It's qualitative data. So you can't make a histogram out of this. But I can organize it into something that's kind of like a frequency distribution. There are things that are going to be definitely different. Like, so for example, there's no real way to order the data on this left-hand side of the column, right? I just have the different flavors that are available, okay? And, you know, if I wanted to, I could put it in alphabetical order, but I didn't, right? It doesn't matter what order you put in here, these things in here, because there isn't an order. This is nominal data. Flavors of ice cream don't have an inherent order. If I was looking at, for example, like the degree that somebody had earned, then there would be an inherent order that I could put this in, but it's still, this data would still be different than the data before that we were looking at. But this is definitely nominal data. And so then to build this frequency distribution, I'm just going to go inside. I'm going to say, okay, how many chocolates are there? 1, 2, 3, 4, 5, 6. How many vanillas are there? 1, 2, 3, 4, 5 vanillas. Strawberry, 1, 2, 3, 4. Mint, 1, 2. And butterscotch, 1. I think I got them all. Okay, and so there's this distribution. And it shows the frequency for each of the flavors, for each of the things that I'm looking at. Again, this tells a clearer story than what I'm seeing over here in just the raw data. That's why we make these things, is because we're trying to understand what is our data telling us. Constructing a frequency distribution is a great way to see what's going on in the data. So these are plotted in what's called a bar graph, and we'll look at histograms and bar graph right now. All right, so our histogram. So I've gone back and I have the data from our heart rate, our resting heart rate stuff. And so here are those ranges again, here are the frequencies. So the way that you build a histogram, again, this only works for quantitative or continuous data, right? It has to be interval or ratio data if you're going to build a histogram out of it. On the y-axis, you're going to plot the frequencies. On the x-axis, you're going to plot the ranges of the things that you're interested in, okay? And so, as I'm building this, you want your plots to kind of fill the graph space that you have, so you need to kind of decide the ranges of the things that you want to build. So I could call this 1, 2, 3, 4, 5, 6, 7. This would be 8. I don't have any values that go that high. Over here on the ranges, I could say, okay, so I'm going to put 0 to 10 here. Then there's 20, 30, 40, 50, 60, 70, 80, 90, 100. And I've got this thing, this looks like a standard graph, right? A histogram kind of feels that way. So then I'm going to go through and I'm going to say, all right, so what values do I have between 51 and 60? Okay, there's 1, so I'm going to go up here, boom, 1 thing in there. Between 60 and 70, there are 7. So I'm going to come up here, that strayed up to 7 and then back down. Despite the poor quality of my sketching, right, these are supposed to be rectangles. Notice that it's continuous, right? They connect. 70 to 80 is 4. So here's the mark for 4. And 80 to 90 is also 4. And 91 to 100, it looks like I have 2. Okay, and there is the histogram for the data that I've collected. Okay, it's a continuous plot of the data, of the ranges that exist within the data that I'm observing. So one of the other things that I wanted to point out is, let's just pretend I had something between 21 and 30. Not that anybody could have a heart rate that low, but let's say that there was 1. I could come over here and put a 1. You notice it's not directly connected to the rest of my data, and that's fine, but it could be, right? If I had, this just says that I have 0 values in between 30 and 40 and 40 and 50, and that's fine, and it's fine to have this lone column or rectangle out there. That's okay. But the deal is that as I'm plotting along, there's a possibility to plot anything within that range, right? That's what makes a histogram is that you use quantitative and continuous data so that data that is adjacent to each other will be touching, right? At these, you can see at these points here that it can make contact. Okay, so that's the histogram. Moving on and looking at bar graphs. So again, here's the data for the ice cream, And your bar graphs are going to plot in a very similar way. So frequency is going to go here. Your groupings are going to go down here. And now it kind of doesn't matter, right? There's no order for the x-axis. Here there is, right? This is going to be a frequency of 1, 2, 3, 4, 5, 6, could go to 7. And then I'm going to go down here and I'm going to put my flavors, right? So maybe in between here and here will be chocolate. And maybe in between here and here will be vanilla. And then maybe over here I'll put strawberry. And then maybe over here I'll put mint. And then out here I'll put butterscotch. But the point is, so my chocolate's going to go to 6. My vanilla is going to go to 5. Strawberry gets 4. Mint gets 2. Butterscotch gets 1. Fill those in. But the difference here is, notice that they don't connect, right? There's a gap between each bar, right? And that's what makes a bar graph different than a histogram. You don't want to connect your bar graphs, okay? Because if you put the bars side by side on a bar graph, that gives the impression that the data is continuous, and this cannot be continuous data, right? Chocolate doesn't like slowly become vanilla, which then slowly becomes strawberry. That's weird. I mean, Neapolitan ice cream is kind of like that, but this is not that. This is something different. So that's what a bar graph looks like, and that's how you build bar graphs. Next type of plot we want to look at is called a stem and leaf display. So you'll see this in the problem sets that you're working on. And what a stem and leaf display does is this. It's another kind of numerical way to build a frequency distribution that kind of plays the same role as a histogram. Now again, we're looking at quantitative numerical data here, right? This is continuous data. And you'll see over here, so number one, why do they call it a stem and leaf display? So first we have the stem, or this is the first digit or digits of the number, and then you have the leaf, which is usually the last digit of the number, okay? So if I had a couple of numbers, let's say I had 67 and 102, if I wanted to chop this up, right, the stem bit of this, so here the stem would be the 6 and the 10, right? For those two numbers, those would be your stems. And then the leaves are the tail end. So here's your leaf. The 7 and the 2 would be the leaf, okay? So as I go through this data set that I have, again, just using this resting heart rate data that I made up, and as I build this, here's my stems. I don't need to include the lower numbers. Your stems do need to be continuous, so I'm going to start at 4. So let's say 4, 5, 6, 7, 8, 9, 10... and then what these stand for, right, that 4 stands for 40. The 5 stands for 50. The 8 stands for 80. The 10 stands for 100. Okay? And now I'm going to go through and I'm going to build my leaves. I probably should have done the stem stuff in yellow. Anyway, so let's go over here and let's build the leaves. So here's a 60. So I have 62. I have 65. I have a 61. And I probably should be putting these in ascending order. And a 67. And look, there's a 66. I think a true stem and leaf plot would start at where it would go 1, 2, 5, 6, 7. But I'm just kind of quickly pulling these out of here. So if I was doing this for an assignment, I'd reorder them so that the least numbers would be to the left. Okay, let's go back. There is a 50 down here. So look, I have a 54. Do I have any other 50s in there? No. Oh, look, I missed some 60s. Here's an 8. Here's a 9. Go into the 70s. There's a 73, another 73. Now, notice I include both of them. You don't leave any of the leaves out. It's okay for it to repeat. A 77. A 78. Okay, and looks like that's that for that. The 80s, I have an 84. Here's another 84. An 86. And an 88. In the 90s, I have a 91 and a 98. And then that's all of my data, okay? So here's what the stem and leaf plot would look like, except for I need to reorder these so that it's least to greatest for the data that's on the left, where the stems represent the tens values and the leaves represent the ones values. And the really cool thing about this is that if you took this and flipped it on its side so that the stems were down here and the leaves were up here, you'd essentially be looking at a histogram of your data. And so that's kind of the cool thing about the stem and leaf display, is that it does include, this does show you all of the individual values within your data, and it gives you an image of what the histogram would look like. Now, if you had thousands of data points, a stem and leaf display would be really painful to build and even more painful to look at. So you'd probably want to just use your standard histogram in that case. But something where you have like smaller numbers of data points, it could be advantageous to you to build the stem and leaf display so that you can see each individual point in the data as you're looking at the plot, which you can't see with a regular frequency distribution. So the last topic for today, we're looking at, or at least the last big topic in this stuff, deals with skewed data. And the way that this works is distributions look different, okay? And there are certain types of distributions that we've given names to. And so when you're building your histogram, and by the way, this skewed data stuff, it only works, most of this plotting really only applies to quantitative data, to interval and ratio data, all right? You've got to have numbers to make plots. So let's take a look at this. So, right, we have frequency over here. We have the category or the grouping on the x-axis. And you may have a distribution that looks something like this. Okay. So that would, there's the histogram, and around that I can plot a distribution that might look something like this, where, a curve that comes up, and so you'll see, right, these are what the distribution curves look like that kind of follow or mimic what the underlying histogram is. And the way that I've plotted this first one is that it's a normal distribution, and you can tell if a distribution is normal or not if you look across the Sorry about that. Had a little technical difficulty. Anyways, so you can tell if a distribution is normal or not by, if you look at down the middle of the distribution, is it symmetric one side to the other? And if you look at this one, I haven't drawn it perfectly well, but you can kind of tell that there is a bit of symmetry there. That to the right of the center is essentially the same as the data that's to the left, right? So this is going to be a normal or a bell curve. There's symmetry in your data. Now, truly normal distributions, have a really cool quality to them that kind of like delineates the breakdown of the data, but we're going to get into those details in a couple of weeks as we dig deeper into the course. But this is your first kind of standard or kind of what to look at is you can say, okay, is the distribution normal or is it a bell curve, right? Does it have that nice, clean, symmetrical shape? So that's, and by the way, normal is not skewed. So we want to look at now, well, if that's normal, well then what is a skewed distribution? So if it's a positively skewed distribution, that means you're going to have a long tail of data on the positive side of the distribution, which means that, so I come over here and then maybe the bump in my data is here, and then it goes out and I have this really long tail to the right. And so what this means is that even though the bulk of my data is here, I still have some points in my histogram that are way out here. And so we call this skewed because even though when I look at this, I can see that the bulk of my data is right here. Next week, we're going to talk about measures of central tendency. And one of the things we look at is the mean, or it's kind of the average of the data set. And all of these large and positive values are going to pull the average to the right, or it's going to skew the average to the right of the distribution. And this is what we're trying to avoid. This is what we don't want to see, is skewed data, because it affects the way that we interpret what we're looking at. Especially because most of the time they don't report the distribution, they report the average of the distribution. And if these data points are pulling my average away from the bulk of the data, I need a way to compensate for that. So that's a positive distribution. The negative distribution, as you can kind of guess, so the negative distribution, let's use orange. The negative distribution, you have a long tail of data on the negative side, right? So this time my tail is going to be over here. Then you'll have the big bump of data. And these guys are going to pull your average to the left or in the negative direction. And so this is what we mean by skewed data, right? What direction do I have? And often these points that are way out here on either side, those are often called outliers. And we want to ask ourselves, right, what direction are the outliers pulling the average of my data, right? What effect do they have on the overall picture of the data that I'm looking at, okay? So these are skewed data sets. The other type of data set that you'll see is a bimodal. And these words will make a little bit more sense next week as we... in week 3, as we look at measures of central tendency. Bimodal means, so, right, the normal distribution comes up and has one bump and is really symmetrical. Well, bimodal means that there are 2 bumps. So you come up and you have like one bump in your data here, and then another valley, and then maybe a second bump in the data over here, okay? So it's bimodal, right? There's 2. You can have multimodal, meaning maybe there are several bumps, but this is what bimodal data looks like compared to a normal distribution. And an example of something that might be bimodal is, let's say, it could be the grades for a class, right? I could be looking at percentages, from 0% to over here at 100%. And, this could be a group of students that has turned in all their assignments and has done everything basically up to par, so you have a big bump of students up here, but then maybe you also have a little bump of students back here. And again, I guess if that's 0 to 100, then this would be 50, and these would be really sad grades at like 30%. So maybe these are folks that, quit coming to class or didn't turn in assignments, right? Something like that. And then you've got... you do have a few students here in the middle. if I was teaching a class and if my grade distribution looked like this green thing, I would be really sad because probably you're doing something wrong as an instructor. Even if I had this red data, I don't want the bulk of my students getting 50%. That would be terrible, right? We would want a distribution, if this was our class grades, that looks something like this, where it came over almost nobody down here, and then maybe the bump is occurring somewhere over here, with the bulk of the class getting an 80 or 90% of the grade, right? That's the type of distribution that I would love to see for our class. And I'm sure that as we go through and we work hard and do all of our stuff, that we can get there. Anyways, this is all I have for this week. Thanks for listening. Send me any questions that you have about this material, and I'll see you in the discussions.